from Earth. It's Space Radio. This is Paul Sutter, and coming up, we're talking about Are We Alone in the Universe? Maybe. James Webb's Revenge, and holy cow, supernova, and of course, taking listener questions about all things in the universe. We record the show every Thursday at 4 p.m. Eastern, so call 888-581-0708 to join the conversation. And in today's Blue Shift, I'll be talking about the tradition of science conferences. But first, the news. Hello, space fans. Welcome to Space Radio. I'm Paul Sutter, astrophysicist at Ohio State, chief scientist at COSI, and for the next half hour, your agent of the stars. Got an exciting show for you today on Space Radio where we talk about all the things. This show lives on listener questions. We record every Thursday at 4 p.m. Eastern here in Studio A of WCBE Radio Columbus. So call 888-581-0708. Light it up. You can also follow along with all the other space cadets on the live streams on YouTube and Twitch. Go to spaceradioshow.com for the links. Joining us on the live stream from around the world, Norg, Netherlands, Texas Hill Country, Fort Pierce, Florida, Central New Jersey, and more. Get those questions in. I've only prepped 10 minutes of show material, so I hope I have something to talk about. And what I want to talk about, I just couldn't resist this topic to go on a rant. You know me, you know rants, we are together. You can't think of Paul Sutter without thinking of a rant. And one of my favorite things to rant about is the Drake equation. If you haven't heard, the Drake equation is a quote-unquote equation that purports to be able to tell you the probability of finding another intelligent species somewhere else out there in the universe. And apparently it's super simple. You count up all the stars. You ask what fraction of those stars have planets, what fraction of those planets have liquid water on the surface, what fraction of those planets have complex organic molecules, what fraction of those can evolve into life, what fraction of those can evolve into intelligent creatures that can make radio and they can start talking to you. And I know I've spoken about it before on the show, but I want to bring it up and again. I honestly think the Drake equation is useless. It is useless. First off, it's not even an equation. It's not even an equation. Real equations relate two different quantities, two different things, and show you how they're actually connected and related to each other and the same. The Drake equation is just a definition. It's an equality. It's if you take a bunch of things and multiply them together, you get the product of that multiplication. That's not much of an equation. That's not telling me anything useful. And the reason I'm talking about the Drake equation is because it's in the news again, where some researchers, some theorists wrote a paper where the paper goes off and says, oh, all previous work on the Drake equation is nonsense. I agree so far, but we're doing it right. We got it down now. We know these numbers. We know their uncertainties, and we're going to plug it in. And when we plug it in, we see that we are totally alone in our universe. It's just us, folks. You and me and Greg are the only creatures in the universe. The hundreds of billions of stars in the Milky Way galaxy, the hundreds of billions of galaxies in the observable universe. That's it. That's it. So I don't know if they're right. I don't think they're right. But every single paper about the Drake equation drives me nuts, because every single paper about the Drake equation is, okay, we're going to take a bunch of things that we don't understand at all. We're going to mush them together and make a bunch of guesses because we have no data, no observations. So we're just going to make it up. And then out pops a number that, seems to oddly reflect the biases that we put into the equations in the first place. So you're not learning anything. You're not gaining knowledge. You're simply taking your biases and assumptions, putting them into a meat grinder, and getting a bias hamburger out of it. You haven't learned anything. You haven't progressed. You haven't made a prediction. You haven't said anything useful. The Drake equation is not helping us advance our state of knowledge of the universe. And every time we use it, we don't gain, we lose, we pull back. And I could go on, but I need to stop because there's lots of cool questions today and I want to get to it. It's time to have a conversation. Before I start taking calls though, whoops, wrong set of notes. We've got a caller. How's it going? What's your name and where on earth are you?
Hello, can you hear me?
I sure can hear you. Coming in a little loud on my speakers, but that's Greg's fault, not yours.
Okay, I have a question about never-scalar particles and like quantum chromodynamics. Like you have those three quarks, and it's totally bound the way they spin, and all those blue ones, and the force that hold them together is supposed to be like 18 tons that are like condensed in that particular area. And with the way I understand, the quarks can only exist as three units, so not just one by themselves. So it makes you think of fields as just energy. So, I mean, it seems to me that quantum mechanics seems to be a pretty provided atmosphere down there.
Yeah, that is a great question. This is so juicy. I love this question because we're talking about the fundamental constituents of matter. We're going deeper than molecules, deeper than atoms. We are going right to atomic nuclei and trying to understand the forces that bind them together. And there is a force that we call the strong force. Colloquially, it's called the strong force. Really, physicists call it the color force for reasons I don't want to get into. But when you look at a proton, when you look at a neutron, it is not an isolated particle by itself. It is actually a bag of other stuff. It's a bag of connected particles known as quarks. And quarks come in groups. The strong nuclear force or the color force is a very, very odd force. It is extremely odd. It is sometimes attractive. It is sometimes repulsive. It has a very strange property that if you take two quarks, which are just named for a subatomic particle, if you take two quarks and try to pull them apart, you're like, I'm going to do it. You grab a quark, I'll grab the other one, and we're going to yank these apart. The farther apart you pull them, the greater the strong force between them becomes. It goes stronger and stronger and stronger. Then it becomes so energetic. The strong force becomes so strong that new particles can be created out of that energy. Just new particles come online out of that raw energy. And those particles will be quarks, and then they'll bind to the quarks that you thought you separated. So just as soon as you split apart these quarks, new quarks pop in, combine, pair up into triplets or more or twins. And so you can't ever see a quark in isolation. And if you think about what it looks like inside of a proton or neutron, you use this word atmosphere, which was great. It is a buzzing, frenetic hive of activity inside of a proton. What we think of as a proton it's not like a ball bearing or a billiard ball or a marble. It's like a sloshing bucket of water with all sorts of complex intertwining interactions that when summed together add up to become what we call a proton or a neutron. Did you have any follow-up questions on that?
Yeah, it's pretty incredible. It shows you just how much we know and what we don't know, like the quantum cover.
Yes.
It's like algebra. You're trying to take three numbers and get a zero, and you can't do it. So they made something up and give them coders to make it white neutral, and that's how they make it work. So, I mean, you can kill.
Whoops. Sorry, I had to cut you off just because you were starting to get a little bit loud, which is not your fault. I'm totally blaming Greg on that. I'm looking at you, Greg. He's shrugging his shoulders. He's like, what am I doing? You're right. I want to make one point before I go on break. it's not that just physicists sit around making stuff up. And it's like, well, I guess we don't understand that, so I guess quarks can't ever, be found in isolation, and that's just the way the universe works. These kinds of models are very, very easy to say. And they're very difficult to prove. They're very difficult to develop from threads of multiple independent lines of evidence, some threads of evidence, some super collider experiments and theoretical expectations all merging together and sloshing back and forth to give us a picture. And so when I say something like, oh, the strong force gets stronger the more you separate the particles, and that's why you can't see quarks in isolation, I'm not just saying that because it's based on, it's our best guess of why you can't pull quarks apart. It is our best guess, but it's our best guess based on evidence. It's our best guess that's anchored in an entire framework, an entire theory that we call the Standard Model. And this Standard Model is able to make predictions about how the universe works and survive experimental tests, which gives us the confidence to make these kinds of statements. So it's not ad hoc. We're not just making up statements as we go. We're building a more refined picture of the universe based on all these threads of evidence and their ability for the models to make predictions that verify against further experiments. That is the name of game of science. Totally. There's a lot we don't understand about our universe, which is where all the fun comes in. But we don't just make up statements because we feel like it. We say statements because the evidence forces us to make those statements. Excellent, excellent question. I love that discussion about the fundamental workings of particle physics. Remember, you can call 888-581-0708 and join the conversation. You can also follow along with the Space Cadets on YouTube and Twitch. Go to spaceradioshow.com. And my name on all social channels is @PaulMetzler. You can follow me there too. This show is brought to you by you. Go to patreon.com/PMSutter because you are making this show happen. See you after the break. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio. We've got some Space Cadet questions ready to go, but you could join the conversation. 888-581-0708. You know what to do, or you can join the Space Cadets on spaceradioshow.com for the links. I've got a question here from Astro B on the live stream chat asking, have I, meaning me, Paul Sutter, ever contributed to astronomy or astrophysics or research? And yes, I have done work in astronomy. I was a grad student at Illinois. I spent 3 years at the Paris Institute of Astrophysics, 2 at the observatory in Trieste, now back at Ohio State. And through that time, I was a very active researcher. I don't want to call myself a good researcher. I'm not going that far. I was an active researcher. I wrote papers. I would give talks. I went to conferences. I refereed articles, all the usual stuff that a researcher will do. And what did I investigate? I investigated a few things. In graduate school, I studied outflows from black holes, specifically trying to understand how active galactic nuclei can potentially magnetize incredible volumes inside of galaxy clusters. After that, in my postdocs, I focused on something called voids. I studied the large empty spaces in between the galaxies, these vast, vast regions of absolutely nothing, trying to understand the nature of dark energy, the history of our universe. Speaking of the history of the universe, I was a member of the Planck collaboration, making maps of the cosmic microwave background, the baby picture, the cute little baby picture of our universe. I've also done work in data analysis of trying to take data of the first generation of stars to appear in our universe when it was just a few 100 million years old, and its effects on the surrounding gas and universe. That is a very, very thorny observational problem, and I was doing some work, and I continue to do some work, trying to develop some sophisticated ways to dig some juicy data out of that horrible, horrible, noisy mess. And I've got a follow-up question from the Space Cadets, Larry Beckham, asking, did I ever get published in Nature? No, and I'm not bitter about it at all. I've not been published in Nature or Science. Most of my papers ended up in the Astrophysical Journal. A good chunk ended up in monthly notices of the Royal Astronomical Society. I've published in Physical Review D, Journal of Computational Astrophysics, a few journals here and there, but not Nature. But I swear I'm not mad about that. I'm not going to hold that grudge, even though they rejected me a bunch of times. But I'm over it. I'm over it. All right? I'm cool with it. I've got another question. Remember, you can call 888-581-0708 and join the conversation here on Space Radio. Or go to spaceradioshow.com for those links to the YouTube chat, the Space Cadets, both on YouTube and Twitch. There's another question here from Thunderduck, which is my favorite kind of duck, asking about virtual photons. And I think this is a good question, following up the discussion that we just had about the strong nuclear force and quarks. And it's just, whenever I get into discussions of the subatomic world, it's known as the particle zoo for a reason, because there is a litany of names and forces and particles and interactions and groups and kinds of particles. And it's really easy to get lost. It's really easy to get tangled up. It's really easy to lose your bearings and just get drowned in the jargon quicksand. And soon enough, you quickly lose appreciation for the beauty and wonder that is the universe. One of those cases, one of these quicksand death traps that I fall into a lot, that I see other people fall into, is virtual photons. I mean, already it takes a while to get used to the concept of a photon, which is a bit of light. Not just any bit of light, but the fundamental bit of light, the smallest bit of light that light can come in. It's a photon, a chunk of light. Then you start talking about virtual photons, and it gets really, really messy. So here's what I tell people when it comes to virtual photons. Don't worry about it. Just don't worry about it. It was a poor choice of wording of the people who first developed this, and we should just move on. We should just move on. I don't have a better name for them, but so in the meantime, let's just not talk about it. Or let me give you some background. So I hope that electricity and magnetism are related. They are two sides of the same coin, known as electromagnetism. Electromagnetism is also known as light. Light is waves of electricity and magnetism. And so light must be related to the magnetic force and the electric force because they're all connected. They're all related. And we have a great classical picture of it thanks to James Clerk Maxwell, developed in the late 1800s. And we have a very, very fancy, complicated quantum picture of this relationship thanks to something called quantum field theory and part of it called quantum electrodynamics. And in this picture, if photons are the fundamental bit of light, like you turn on a light, there's a bunch of photons streaming into your eyeballs, then the electric force and magnetic force are said to be communicated by virtual photons. Because it's not like you see little laser beams when you hold a magnet up to a fridge. You don't see a bunch of laser beams bouncing back and forth between the magnet and the fridge. So photons are out. So we just say they're virtual photons. And that's how magnetism happens. It's more complicated than that, but it's also kind of simpler than that. There is an interaction between your magnet and your fridge. This interaction can be described with quantum mechanics, with quantum field theory, with these very esoteric, deeply mathematical models of our universe. That interaction kind of, sort of, maybe looks like tiny invisible photons bouncing back and forth, but it's not quite. So take a step back. Instead of saying virtual photons, we're just going to say that there is a quantum interaction connecting your fridge magnet to your actual fridge. and the rest is some pretty insane mathematics. So I know that's not a very satisfying answer. I do have an Ask a Spaceman episode on it that I spend something like 45 minutes digging into this. So go to askaspaceman.com. That's my podcast where I dig deeply into topics like this. I did an episode on virtual photons and digging out the mathematics as best I could. Go ahead and give that a listen if you want. We're almost out of time today on Space Radio, but before we go, it's time for the blue shift. I'm messing up all my notes. They're all out of order. Sorry, Greg. I'm Paul Sutter, and you're listening to Space Radio, and this is the Blue Shift, my opportunity to get a little bit closer to you. And this is a topic I wanted to bring up a couple weeks ago, but I instead answered a bunch of questions. But I want to talk about like science conferences and the need for communication. Like I talk about the paper, the Drake equation stuff. I talk about my own research today. I talked about, how we develop models of particle physics, everything from the strong nuclear force to virtual photons. And there are a lot of papers written just in astronomy. Just in astronomy, there are about 40 to 50 papers in astronomy written every single day. Every single day. And you can subscribe to the list of papers that have been submitted for publication so that every morning, every astronomer wakes up to the list of papers written the day before and submitted for publication. And there's like on average 40 to 50. That's a lot of papers. That's way too many papers to read because you'd spend all day reading papers. So we meet. We go to conferences. We talk it out. And I'm sure you, in your business, in your profession, have conferences. An academic conference is a little bit of a different kind of beast. There's still talks, but there's a lot of hallway conversations. There's a lot of coffee chats. There's a lot of questions after a talk, during a talk. There's a lot of debate. There's a lot of arguing. It is a forum for exchanging ideas, for presenting your idea, defending your paper, fleshing it out, hashing it out, letting the detractors detract, defending it, letting the audience decide, trying to convince other people to follow along in your research or cite it, or trying to discourage people from following the research of your rivals, all the good juicy stuff and drama and politics that happens. The real meat of science happens in-person interactions, even though it's the 21st century and we have Skype and we have Zoom and we have YouTube and we have chat. The in-person interactions are where the magic happens. And speaking of in-person interactions, if you would like to have an in-person interaction with me and the sky, save the date for Friday, July 13th at the Hocking Hills. We are going to have a cosmic cookout. So there's going to be food. There's going to be me talking. We're going to go to the John Glenn Astronomy Park in Hocking Hills. We're going to look at the stars. We're going to get a sky tour. I'm going to talk some more. Probably going to talk a whole lot more. It's going to go pretty late. It's going to be lots of fun. Details will be available on WCBE.org. But in the meantime, just save the date. Save the date for Friday, July 13th. And unfortunately, this broadcast is almost done. Thank you for joining me on this voyage of space radio. Once again, I'm Paul Sutter, and this show is brought to you by the Ohio State University Department of Astronomy. Learn more at astronomy.osu.edu. This show is also brought to you by you. Can't say it enough. You mean the world to me. Patreon.com/PMSutter to learn how you can contribute. Thanks to Greg Moebius for producing, Dan Michalko for being awesome, and all the fine crew at WCBE Radio for making this show possible. We record every Thursday at 4 p.m. Eastern. Call 888-581-0708 to join the conversation. And you can also join the Space Cadets on YouTube and Twitch. That's spaceradioshow.com for the links. You can also follow me on Twitter and Facebook. My name is @PaulMattSutter. And of course, thanks again, Earthlings, for listening. See you next week. And remember, science is for sharing. End of transmission. We got a caller, but
I know.
We're done. Sorry, caller.
You want to talk to him for a second? Okay, what is the nature of your coin?
We'll catch you next week, caller. Sorry, someone called in just at the last minute. And Space Cadets, what should I call this episode? Thunderduck, there it is. Ask a Spaceman number 35, all about virtual photons. Slinker Deer, I'll let him come back next time. Oh, Constellation Pegasus, that was you. You should have said I know you from YouTube. I get it. I know you weren't trying to denigrate physics or anything. I just wanted to use the opportunity to create a point for the audience. So totally understood, no hard feelings, and thank you for the very, very cool question, Constellation Pegasus. And you were super loud, but I am blaming Greg for that, not you. The Drake anti-equation. That's a good one. That's a good one, Larry. I like that. The Drake anti-equation.
That was a shame. He was from Stockholm.
Oh, no way. International caller. The caller was from Stockholm. Man. Next time.
Yeah.
I'll get you next time, Gadget. Grab a particle drink at Quarks Bar. I like the Drake anti-equation. That just tastes good. That one tastes good. All right, Space Cadets, I gotta go. Until next time, thank you so much.